right, so remember the challenge we gave you yesterday? That we need to print a countdown, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then when we get to 0, instead of printing out 0, we need to print blast off. And the challenge is to do it with no loop. We're not also going to hard code it, so we're not just going to have 11 print statements or something like that. But we are going to have, we can have if statements, conditionals. We could have variables. We could have functions. What if I gave you a function that did it part of the way, right? So int or void, let's say, countdown, right? Countdown. And it took an integer here, n, right? Now, remember, it's going to count down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So if it's 0, right? Let's say that if n is 0, then instead of printing the number, we're going to print blast off. Printf blast off. Right? That gets part of the job done, right? And if it's not 0, if it's 10 or 9 or 8 or 7, et cetera, right? Then we'll go ahead and else print the number. Printf the number here, %d, and the line n, okay? Now, if I just called this from the main, countdown, where would I start my countdown? At 10, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, all right? So we'll put in 10 here. Now, what is this going to print? This is not going to get me all the way there. All it's going to do is print 10, all right? So I have a function that will print a number in the countdown, but if I only have one call to it, then it would be 10. Right? Now, no hard coding of this either. If I just go countdown, that's not what I want, but if I just go countdown 10, or not Korean house, somewhere I was searching up in Omaha, countdown 9, it was a restaurant, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I haven't gone there, but it was suggested. I'm going to check it out. Anyway, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. No, that's hard coding it as well. Right? Well, think about this as a function. Well, I've got a function that will print out the number depending 10 or 10 to 0. What else could I do? What if I called the function up here instead? Right? So if it's 10, I'll print out 10. But then I want to go down by 1. So what if I did n minus minus, and then I called this function again, countdown. Right? That countdown function on that decremented n, right? That's going to give me, that's going to print out at 9. Well, it's not equal to 0. So what happens? We go into this code part, this code block. Then we decrement it again. So it was 9. Now it's 8. 6, 5, 4, 3, 2, 1. When does this stop? When we get down to 0 and it prints blast off. Should I make any more function calls at that point? No, I'm done, right? So I'm going to reformat this a little bit, and I'll just go with the -1 directly in there. Now let's see how this works. Go back into my lecture, CSE, there we go, GCC, a demo. All right, and let's run this. Hey, it was achieved. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Now, before we explain this further, let's visualize it and see what's actually happening here. Oops, nope. Edit this code. There we go. All right. Let's understand what's going on here by looking at the call stack. Right? So when we call countdown 10, a new stack frame is created on top of the stack that receives a value of 10. Right? That's not equal to 0, so we go to the second block there. We print it out, and then we call that function again. What's going to happen now? Another stack frame is going to be on top of that, right? That receives the value 9. Right? Likewise, it goes down to 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Right? Now, what's going to happen at the end here? Right. We've got 10 stack frames here, each one of those holding the value 10 through 1 here. Right? We're going to create one more stack frame that receives the value of 0. Right? It did go in there. There's 0. Right? Now we're going to no longer make those function calls. Instead, we are going to print this out, blast off, and then start returning back from our function. What's going to happen to each one of these these stack frames as we return? They get wiped. What was that called? There are two operations on a stack: putting something on top and then taking it off the top. What is the putting on? No, that's a smashing event, right? When we destroy the stack and we got a stack, we push it on the top and then we pop it off the top. Just think of the dishes at your not cafe, but the dorm room, whatever it is, right? The buffet. It's got a spring-loaded thing. What are you doing when they bring out the clean dishes? What are they doing? They're pushing them on top of the stack. And then they've got these tabs that hold the dishes so that the spring doesn't just shoot them all out. You're popping it off the top. Those tabs get popped, right? All right, so it's going to start popping these off the top. That seems weird at first, but it's called recursion. Recursion is any time that something is self-referential, right? Recursion is something that references itself. Now, in coding, a function is recursive if it makes one or more function calls to itself. In this case, we had countdown makes a recursive call to itself over here. Right? And so it's going to call, the function calls itself. That makes sense because any function that we've written so far can call any other function. It just makes sense that you can call yourself. Right? It's just called recursion in that case. Right? You've probably also seen this in mathematics, right? Fractals. You've seen fractal art, the Mandelbrot set, or the Sierpinski triangle, Mandelbrot art. Right? You can just look at this. Those are self-similar. There's the Mandelbrot set right there. Right? It's defined as self-referential. Here's an easier way to do it. Sierpinski triangle. This is an even easier visualization here. How does it work? Well, you take a triangle and then you remove the inner third, or inner fourth, I think, right? That triangle right there. And then you recurse on it. You go then to each one of those three triangles and you remove the middle part of it. And then you keep going at infinitely more, right? So it's the same rule applied multiple times to itself. Here's the progression right here. Where you're removing the first one, then those three triangles, you're removing the middle, then those... Now, how many triangles do we have now to remove? 3 times 3 is going to be 9. 3 times 3 times 3 is going to be 27. 27 times 3 is going to be 81. 81 times 3, ... Right? It's an infinite progress, right? You no matter what, if you zoom in on any one of these triangles, it's going to look exactly the same, right? That is self-similar objects, self-reference. You've probably also seen it in mathematics with respect to the Fibonacci sequence. Here is the actual definition that we'll use, right? It's a sequence. It starts out at 1, and then the second one is also a 1. So f of n being 1 will give you a value of 1. F of 2 will also give you 1. But everything after that is going to be the two previous values in the sequence summed together to give you the next one. So if we were to calculate this, right, we'll do it. The first two values are 1 and 1. Right? What's the value after that? You take the two previous values, which is 1 and 1, and you sum them together to get 2. The next one is the two previous ones, 1 plus 2, so it's going to be 3. 5. Now the two previous ones are 3 and 5, so we go to 8. 13, right? 21, 34, 55, 89, etc. Right? Off into infinity. It's a sequence. It's an infinite sequence. Right? And you can see that it's growing very, very fast there. Right? So you've seen this before, even if you didn't call it recursion. Anything that has a self-reference is recursive. And in code, that means a function is going to call another function. So how do we go about designing functions? Every recursive case needs a base case in which no further recursion is needed. Because what if you didn't have a base case? For example, let's come back over here. What if I did not have this base case right here? Yeah, let's observe that, right? I'll get rid of that, All right. Print 10, go down to 9. Print 9, go down to 8, right? What's going to end up happening here? You said it, infinite loop, and we're just going to keep going off into negative infinity. Without a base case to stop this, we're eventually going to, why did that happen, by the way? Stack Overflow, exactly, right? Because we are putting frame on top of frame on top of frame on top of frame. We did that 261,744 times, actually plus 10. Right? So about 250,000 times. That tells you how big your stack is, right? Eventually, we'll overflow it. Right? So you need a base case in which no further recursion is performed. Right? Some base cases may be for error handling. Right? So, for example, if it was more than 10, or if it was already negative. Let me go ahead and restore that, right? If it's 0, whatever, that should be an else if, right? Let's do some basic error handling here. If n is greater than 10 or n is less than 0, then we'll say printf error, because we don't allow that kind of countdown, and then we'll say else if, right? And now if I were to call this with, say, -10, right? GCC, then I'm just going to get an error and stop. Okay, no further recursive calls on that. Print it out. Actually, generally you don't print errors with error handling, but this is for demonstration purposes. All right. The second thing that you need is that you make one or more recursive calls that must make progress towards a base condition. What if you do not make progress towards a base condition? Right. Here, I'll start it out at 10 again. And what if I just called it on n? Right. I'm not decrementing n at all now. It's going to print, it's also going to be an infinite loop. What's it going to end up printing now? 10, 10, 10, 10, 10, 10, 10, 10, 10. Because I'm not making progress towards my base case. Okay? All right. Then finally, you invoke, you get the recursion started by calling the function on an initial value. All right? Okay? So those three things right there. That sounds weirdly familiar. You have a base case where you stop. You make progress towards that base case. And then you have to have a starting point. Where have we seen these three elements before? No? An initial condition? Loops, period, right? Right? You've seen this before, right? Loops, right? So we're not using a loop, but we're basically abusing the call stack to do our loops for us, right? We're letting each one of those stack frames keep track of an index variable, right? A base case is basically equivalent to, almost equivalent to, a continuation or termination condition. Once you reach that termination condition, then the loop stops. Right? Progress toward a base case means that you are making is the same thing as making progress toward a terminating condition in a loop. Right? And then finally, the initial value. Initial value. This is equivalent to value is equivalent to the loop starting point. In other words, int I is equal to 10, right? While I is greater than or equal to or greater than your 0, right? I minus minus. Each one of those three conditions that we just wrote out in a recursive code can be translated over to a simple for loop, right? So, why do we need this if we've got loops? Well, let's look at the good parts, right? Recursion can be useful or good. That's kind of a value judgment. Many divide and conquer algorithms are presented recursively. So, for example, you've got this complex problem, like, say, sorting an array. I don't know how to sort this thing. But if I split it up into two arrays, well, now I've got a smaller problem, right? If I had 10 elements before, I don't know how to sort 10 elements. So let me go ahead and divide it and conquer it. Now I've only got 5 elements to work with, right? I only have to sort 5 of these things. That's still too much. I don't know how to do that. So I'm going to divide it and conquer it again. And now I've only got 2 elements, right? I could take the min or max, right, of 2 elements, or better yet, divide it one more time, right? 1 element. If you wanted to sort an array of size 1, is there any work to do at all? no, it's sorted already. So many divide and conquer algorithms will be presented as a recursive approach, okay? Where you want to make two recursive calls, one on the first half and one on the second half. We'll look at examples later on. If you're mathematically inclined, it's a good way to think inductively. Not many people are probably taking 235 right now, but you will next semester. That's discrete math. And one of the proof techniques that you'll go over is induction. Induction, you've got a base case where you prove it for one element. And then you've got an inductive step where you say, okay, suppose that it holds for n. I'm going to prove that that implies that it holds for n plus 1. And because you've got this base case over here, all you have to do is recurse back to the base case and you've got a proof. Right? That's induction. Many functional programming languages do this as a matter of course. If you've ever seen Haskell, Scheme, Lisp, these kind of functional programming languages, they do not even have loops. Right? They don't have for loops or while loops or anything like that. You have to do everything recursively. In fact, a lot of them don't even have variables. Right? They just have parameter variables. There's not like a variable you can set int x is equal to 42. They don't even allow that. Right? And it forces you to think like a mathematician instead. Right? I don't think mathematically like that, even though my undergraduate was in mathematics. Right? I still like to think sequentially. I still like to think, imperatively. But there are languages like that. Right? A recursion can also be lead to simple or clean or beautiful or easily understood code. Right? Now I put all those things into double quotes there because there's a value judgment here. Right? Right? Let's come over here and look at an alternative here. For int I equals 10, I is greater than 0, I minus minus. All right? Printf, %d, and the line, I. And then after this, printf, blast off. Right, there we go. All right. You tell me, is this beautiful? Or is this beautiful? Right? Okay. It's in the eye of the beholder. I think that this is simpler, this is more beautiful, this is more understandable versus something like this. Now, if you were so inclined and you loved recursion, then yeah, okay, wow, this is beautiful. This is simple because I can use a divide and conquer strategy. All of these things are subjective. Right? It's in the eye of the beholder there. Right? So I don't buy those arguments. Right? I buy the arguments of recursion, the bad. Okay. Well, first of all, we've already seen one risk, right? If you have runaway or recursion, or even if you have a deep recursion, you risk a stack overflow, right? Maybe I wanted to do a countdown of 300,000. I wanted to go do 300,000 things. The stack would not allow me to do that. I would immediately hit a stack overflow, and then the show's over, right? Even if it isn't runaway, you're still abusing the stack. The stack is small and helpless. Don't abuse it. Right? The heap is large and can take the abuse. So if you need to do something, do it in the heap. Right? We're abusing the stack space here to do something very simple of keeping track of an index variable, I. Right? Why do we need 10 copies of 10 variables in 10 different stack frames when all we need is one variable in one stack frame? Right? That's simpler. Most or all recursion can actually be rewritten. In fact, most of it is as a regular loop or something that simulates recursion. The prime example of something like this would be quicksort, which we'll look at starting next week, where we'll look at searching and sorting, where it takes that idea of dividing and conquering. Right? Well, usually the algorithm is presented in a recursive manner, but nobody would actually code it like that. Instead, what they do is they simulate the recursion using an in-memory stack on the heap instead of abusing the call stack. Right? And then, of course, you also risk exponential blow-up, right, with a problem. To understand that, what I want to do is I want to go back to this perfectly bad example. Right? So anytime you see recursion, somebody's going to pull out the Fibonacci sequence. That's the immediate first thing that you see. And I hate it. Because what good is the Fibonacci sequence? Does anybody know? Does it have any practical applications? No. It might. You might have seen something like the golden ratio, something like this spiral thing. There's the golden ratio. Maybe there's a picture to go along with it. Maybe that. Okay, that's not going to animate. All right. What if I search for pictures? Mona Lisa. Yeah. This spiral thing. Perfect. Proportions or whatever, right? I'm not an artist, so I don't know how much of that is BS or not, right? But I do know that there is nothing going on with this Fibonacci sequence. It is a linear homogeneous recurrence relation of degree 2. There are an infinite number of them, right? And there are much more interesting sequences out there. So why do we obsess with this? I like it because it serves as a perfect bad example of why recursion is bad. Right? Let me show you. So blast off stuff, we'll go ahead and get rid of that. That was just demonstration. Let's go ahead and write a function to compute the Fibonacci sequence as an integer. We'll just do integers here. Fibonacci, right? Okay. There we go. There's a name for some guy that nobody cares about, right? All right, so we'll take an input here in n. Right? Now, here's the definition. If n is 1, I will return 1, right? So, if n is equal to 1, then I will return 1, because that's the value of the sequence. Now, if n is 2, then I'll also return 1. I could actually collapse that down into one check, right? Maybe I also want to do some error checking here. Right? If n is less than 0, it's undefined. Return -1 or something. Some sort of flag value to indicate I have no idea what that is. That's not well defined. Okay? There's my base case. That's always the first thing that you do. When you go into a recursive function, the first thing you need to do is identify the base case, because you don't want an infinite loop. You don't want a stack overflow. So that's where we stop and no longer call any recursive functions. Else, if it's greater than 2, then we define it as the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Right? And so I'll return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Right? That's beautiful code, right? Its beauty lies in the fact that it has just a one-to-one correspondence with this mathematical definition, right? That's not beauty in my book. That's just straightforward coding, right? Let's see the consequences, okay? Int n is equal to, let's go with 10, right? Actually, let's keep it small, 4, right? Int result is equal to a call to Fibonacci of n, and then let's print everything out. Fibonacci of %d is equal to %d. Right? There's n, and there's the result. Right? GCC this. Fibonacci of 4 is equal to 3. Remember, it started at 1, 2, 3, 4. Did it match? Yay. Let's try something larger. 10. Did we go 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should get 55. Right? So run this. 55. Looks like it works. Right? Let's go to 20. Okay. Let's go to, I don't know, 40. Oh, it actually went. Okay. Fine. I'm going to have to go to, you are too quick for today. All right, there we go. Certainly up to 50 here. All right. So how long should I wait for this? Well, let's see. 2 to the 10 would be 1 million. The first one, the last one, 40, that executed in maybe, let's just say 1 second. It was quick, right? 2 to the 40, 2 to the 10 times that. So let's go to Wolfram Alpha here. What is 2 to the 10? Actually, it's going to be the golden ratio to the 10 times 1 second. How many seconds is that going to be? This is just a quick estimate here. Okay, that's going to be about 2 minutes. All right. Okay. Are we going to get that? This is just a really, really bad estimate. I don't want to wait that long. Let's go up to 60 here. Right? Now, we are going to have overflow here because it is a large number, but that's okay. It'll still at least compute. That's going to be 2 times. So the golden ratio up to the 20. That's going to take 3 hours. Right? What if I went up to 70 here? And so I'm going up yet another order of magnitude here. Right? I'll explain the math later maybe. Right? But there, if I did that, I'd be waiting weeks to get my answer back. Right? Wolfram alpha, what was it, the 70th Fibonacci number? What is the 70th Fibonacci number? Right? There it is. It's not that big of a number. Right? Now, we would have overflow from this number, but we should not be waiting 2 weeks to compute such a small number. Right? But we will be. Right? Now, let's understand why this is. Okay? And unfortunately, I don't... where's my... I thought I had a... I should have brought my iPad. We're very quickly going to be going to a point where I'm going to start drawing stuff. And I should have started bringing my iPad with me, but I didn't. There we go. Here's the Fibonacci tree, though, already pre-written. Okay? So when you're calling Fibonacci of 5, think about how this works. It's going to make 2 function calls. One of them with 5 minus 1, which is going to be 4, and another one with 5 minus 2, which is 3. Well, each one of those calls is going to make 2 recursive calls. Fibonacci of 4 is going to make a call to Fibonacci of 3, Fibonacci of 2. Fibonacci of 3 is going to make a call to 2 and 1. Right? 3 is going to make a call to 2 and 1. 2 is going to make a call to 1 and 0, and that's where it stops. 1 and 0, etc., etc., etc. Okay? Now, how many times was Fibonacci of 2 called? Let's go. How many times was Fibonacci of 4 called? Actually, let's start at the top. Right? Let's make notes of this. All right. So number of calls. Right. So Fibonacci, and here I'll shorten it here. Right. Fibonacci of 5. How many calls did you see in that? Just one, right? Way at the top. Right. Okay. All right. Well, what about Fibonacci of 4? There's only one call there, right there. Right? Now, what about 3? I count 1, 2. You see any others? Okay. We're good. Fibonacci of 3 is going to end up having 2 calls. You start to see a pattern here. Fibonacci of 2, how many calls was that? Let's count them up. 1, 2, 3. Is that it? 4. Twos. 1, 2, 3. There it is. Did I miss them? No. Okay. So there's 3. All right. All right. What about Fibonacci of 1? Yeah. Don't even bother looking at them. You can predict. 1, 1, 2, 3. Have we seen that before? There it is. 1, 1, 2, 3. The number of calls that we make follows the sequence. Now, let's come back over here to Wolfram alpha. Right? If I wanted the 70th Fibonacci number, I would be making about that many, actually an order of magnitude greater. I'd be making that many function calls. How many is that? There, and there. Do we have a name for this? There we go. 190 trillion. 190 trillion things, right? And not only that, but most of them are going to be repeated. When I get down to Fibonacci of 1, I will have computed that billions and billions of times, over and over and over again. In other words, I've got repeated work here. Right? The repeated work is going to be exponential. Right? A blind recursive version of this makes trillions of function calls. Right? An exponential amount of work. Right? It's going to be related to that golden ratio there. Right? That's 1.6 raised to the power of n right? Where n is the Fibonacci number that you're trying to compute, somewhere around there. Okay, there is a closed form solution of this, right? Not only that, but a lot of the work, and in fact, most of the work is repeated, right? The same values are computed over and over and over, right? We don't like that because why are we wasting our compute power to do the same work over and over and over again, right? So there's the bad part of recursion, right? Everything good about it is kind of subjective. Do you like it or not? But everything bad about it is absolutely objective, right? I can compute Fibonacci using a loop way faster than you could ever hope to do it recursively, right? How would I end up doing it, by the way? Int value is equal to 1, right? All right, here, let's go with A and B. A is equal to 1. Int B is equal to 1. There are the first two values, right? And for int I equals 2, I is less than or equal to n, I plus plus, right? What I'll say is int C is equal to A plus B, the two previous values there. And then I need to set myself up for the next loop. So I'll get rid of A by making it B, and then I'll get rid of B by making it C, and update those as we go along. So it's basically a window. I've got two values, the previous values. To compute the next one, I have a temporary value here, and then I move that window over, right? And this is only going to be n, right? 70 computations instead of that 190 trillion, right? I am orders and orders and orders of magnitude faster than that, right? Okay, so there's my solution of just using a loop to do it, okay? So the question is, if it's bad, how do we eliminate it, right? You can always, right, almost always, use a regular old loop and data structures to simulate recursion. Like I just demonstrated, you don't have to write a recursive version of Fibonacci. All you have to do is write a loop to do it, okay? There's another technique called tail recursion. This eliminates multiple stack frames. In other words, the compiler can optimize your recursive code away and use only one stack frame, right? So you can write recursive code if you think it's beautiful, and then the compiler, which doesn't really care about recursion at all, it cares about speed, it's going to take your code and it's going to transform it so that it's not actually recursive, so that you're using this one single stack frame over and over and over again, right? The one that we're going to look at, though, in depth here, and definitely on Monday, is going to be memoization, right? The idea here is go ahead and use recursion, but you don't recompute previously computed values. Right? In other words, if you compute Fibonacci of 1 once, don't compute it twice. Instead, store it somewhere. That's called caching. You cache, that is, store results so you can reuse them. Right? And this technique is used all over the place. Suppose that you're making a very expensive call to an API, literally expensive because you're paying for this. For example, you're making a call to, I don't know, Yahoo Finance because you're pulling in updated stock data, right? And you're querying their web service thousands of times every second because you're trying to do mass quantity trading or something like that, right? You try to store the most recent result so that you don't have to do. I mean, maybe that was a bad example because stocks are very volatile. But if you are using, say, Google Maps, you do have to pay for Google Maps API. And the driving distance between two locations, that doesn't change every microsecond. So compute the driving distance between two locations and store it so that you don't ask them multiple times. Because each time you make a query to Google Maps API, right, as long as you're paying for it, that's going to cost you, right? Same thing with any API out there. Every API is now charging you, right? And so you don't want to make multiple calls out there. You make one call, great, I got the result. I'm going to store that so I don't have to make another call to that API. Application Programmer Interface, if you've never heard of that. Basically, you're just pulling data from some service somewhere, right? And so you're going to cache that and store it, right? Here are the basic steps that we're going to use to improve that code, right? What we're going to do is we're going to maintain a table or cache of results. And now when you're actually using memoization, by the way, memoization, that is not a misspelling, that is not a mispronunciation, that's what they call it. They had to invent a word because we thought of something cool and new, and so we're going to just call it memoization, not memorization, it's memoization, right? Don't ask me why they did that, right? They thought they could patent it or something if it had a new name, right? And when you use memoization, you sometimes get really fancy, and you call these things tableaus, if you could spell it correctly. Tableau. There we go. That looks better. A tableau. Right? Actually, there's an IBM product called Tableau, isn't there? Like for data visualization and stuff like that. And people use it all the time. And so it's a fancy word for table, right? It's not even really a fancy word, isn't it? Just French? French speakers out there? No? Okay. All right. So we're going to maintain a table or cache of results. Initially, it will hold dummy values and indicating not yet computed. Right? So we have to know, has this value that we're going to look up in this table, has it been computed or not already? And if it's not been computed, then fine. We're going to go ahead and use recursion, and we're going to compute it. Right? If not computed, use recursion to compute, and then store it back into the table. So that next time you come to the same value, you look at the table again, oh, it's been computed. We're going to go ahead and pull that value out of the table instead of making all of these recursive calls. Right? So look it up. If computed already, the value will be used. Right? In other words, we pay for the recursion when we have to, but we don't pay when we don't have to. Right? It's pretty straightforward. Okay. We're not going to be able to do it all today, so I don't really even want to get started because we're not going to be able to do anything on Friday. Remember, there is no class on Friday. There's no live stream on Friday because I've got a college committee meeting all day. I don't want to be there, but sure. Anyway, we'll come back on Monday, and that's where we'll get started. We're going to revisit this problem, and we're going to use memoization to solve this. Okay, following these steps. All we're going to do is we're going to put it in a table, look up values, compute them, put them back into the table, and we'll be able to compute all these things. In fact, I don't even know if we're going to use Fibonacci. We might do something more fun. No, we'll do Fibonacci. Right? We can do some other things. Basically, any recursion that looks something like this would follow from it. Okay? All right. So I'll see you on Monday.